Okay, so today we're going to have a second lecture on the deBroglie-Bohm interpretation, and I'm going to tell you a little bit more about the interpretation, and then I'm going to talk mostly about various criticisms and the responses to those criticisms. So I have to review what we saw last time, just to sort of freshen your mind. So here's the deBroglie-Bohm interpretation for many particles. The idea was that the ontic state, the complete description of reality, was not just the wave function over the configuration space of those particles, but it included a Bohmian configuration, which is a specification of the positions of each particle. And then the evolution equations were that the wave function evolves just according to the standard Schrödinger equation, and the particle positions, the Bohmian positions, evolve according to these equations, which are called guidance equations, specifying the velocity in terms of the gradient of the phase of the wave function in the configuration representation, evaluated at the Bohmian positions. Remember that my notation is that R is the magnitude, the modulus of psi, and S is its phase. Okay, I mentioned that one of the assumptions of this model is that if you ask how are these Bohmian positions distributed, you assume that at the beginning of time, for example, they're distributed according to psi squared. And if you assume that this is true at any time, then you can prove that it's true at all times. We had this important concept of occupied and empty waves. So if I decompose the wave function into a sum of terms, if the Bohmian position is inside the spatial support of one of those terms, then I say that term's occupied. If it's not inside the spatial support of some term, that term is called an empty wave. And if just one of them is occupied, then the guidance equation depends only on the kth wave. If two of them are occupied, then it depends only on those two waves, and so on. Okay. Finally, I showed you that if you have two particles whose wave function is a product state, like phi tensor chi, then you can work out what the phase of the overall wave function is. And you can show that the evolution equation for the first Bohmian position depends only on the wave function phi and depends only on the position of the first particle. So, and similarly with the second particle. So the particles will evolve totally independently in the case of a product state. And therefore, in the case of an entangled state with just one wave occupied, right? So that term in the entangled state is a product state. I'll find that they evolve independently. And so where we ended up last time was showing that you could reproduce the operational predictions of quantum theory using Bohmian mechanics. And the idea was that if you have your system, phi k's are some eigenstates of an operator on the system, chi is an initial eigenstate for the probe, and eta describes some environment having a large number of degrees of freedom, then if your measurement works well, the probe comes to be in a different state depending on the system, and the environment also comes to acquire information about what the state of the system was. So if you had a coherent superposition of system eigenstates, you get this big entangled state. And then critically, most environmental interactions will not just carry away information about the system's observable, but it will encode that information in position degrees of freedom. So, my example was imagine a needle, which is a pointer. If I shine light or air molecules on that and they scatter off it, typically the information about which way that needle was pointing is now encoded in position degrees of freedom of the environment. And therefore, for different values, j and k, those eta wave functions are going to be close to disjoint and non-overlapping. And that's important because although we showed even without the environment that the wave function that was relevant for the future dynamics of the system was just the occupied wave. So for example, if the Bohmian position ends up in the jth wave of this superposition here, so for the moment, suppose there's no environment. So it ends up in the jth wave here. So phi j is sufficient for calculating the dynamics in the future. But the problem is that the other phi k's could come to re-interfere with phi j, and then we don't quite have the predictions of operational quantum mechanics because we don't have the irreversibility of collapse that we see in the operational theory. However, when you include the environment, the practical problem of making sure that all of these different empty waves, these eta k's, come and re-interfere, or even two of them come and re-interfere when you've got, say, 10 to the 23 degrees of freedom in here, that just becomes completely impossible. And so in practice, you have an irreversible collapse. OK, so that's where we left off last time. Are there questions about this? Yes?
So I was thinking about this a little the other night, and I was wondering, with all of the technology that we have today, could you set up in the lab some sort of quantum experiment like IQC where you isolate something really carefully from the environment and then try and see whether you ever get things recombining back so that then you could tell this interpretation apart from the usual interpretation of quantum mechanics? Or is there literally no experimental circumstance under which you could ever tell the difference?
Well, this interpretation is meant to reproduce exactly the predictions of the standard quantum theory. So I don't know exactly how you would tell them apart. But,
well, I mean,
yep.
Like if you engineered a system where you don't have that kind of decoherence into the environment, then would it make different predictions?
Well, certainly if you say, I think the place where people really ask this question is about collapse theories, which we're going to see tomorrow. And let me sort of set collapse theories against both operational quantum mechanics and the Bohmian interpretation of quantum mechanics, sort of, because they end up in sort of the same camp. So the collapse theories would say something like, if I manage to entangle some microscopic system with a large number of other microscopic systems, such that the whole entangled state involves an extremely large set of components, then according to the collapse theory, that thing doesn't evolve unitarily. It's going to evolve very differently because of a collapse mechanism that causes it to actually lose coherence. Whereas both operational quantum theory and Bohmian quantum mechanics are going to say, if you somehow manage to do the really hard task of re-interfering all the wave function for all of those guys, we predict that you're going to see interference. So in that sense, Bohmian mechanics is not making any sort of new sorts of claims. Even the operationalists would say that. It's only the collapse theorists who say, no, the collapse mechanism is really a dynamical, irreversible process. And it happens by virtue of systems being very large and having lots of components. They're going to disagree. So when I said that operational quantum mechanics posits irreversibility, I didn't mean that this experiment you described wouldn't come out the way unitary dynamics says it would, but rather just in practice when we do experiments, we don't ever find that we can reverse it easily. Why is that? And if Bohmian mechanics didn't accord with that practical irreversibility, we'd have to say, well, it wasn't really doing justice to operational quantum theory. Yes?
Yeah, could I ask, so what, how is the first line determined? Like, how do we say that, why do we say the measurement of the system A necessarily means this goes to this? Because I see that, one could also say that the system, the wave function of the system itself that you're measuring also changes to something else.
That's true. A more general model of measurement would allow for the final state of the system to be different. And therefore, instead of getting a projection postulate at the end, I could get any other kind of update rule. So we talked a little bit in the first week about how, for instance, after the end of the measurement, I could do a unitary, which rotates it. So I could certainly write down a measurement model that would incorporate that unitary, and then it would have the different projection postulate, or the different update rule. Or I could even imagine one where the system's just completely destroyed at the end. So there is no R system left, like a photon, which gets absorbed. To some extent, that's not so important here. This is the Bohmian story that you'll read typically always refers to this projection postulate, that type of collapse. But even if the system were destroyed, you can still ask the question of, what is the probability of getting outcome K? In that case, this will get it right. It'll just be the mod squared of CK. And if the system isn't destroyed and undergoes some sort of update map, you can always ask, does Bohmian mechanics get the update map to be the same as what operational quantum theory predicts? And a more involved calculation will show, yes, it does. So even if I'm measuring a POBM and I have some funny update map, Bohmian mechanics can reproduce that. And one way to see it is that, as we discussed briefly in the first week, any POVM and any update map, which was a set of trace non-increasing completely positive maps, each element of which were associated with an element of the POVM. So that's kind of the most general way of representing a measurement. Every one of those measurements can be implemented by doing a unitary coupling between the system and some apparatus, and then doing a projective measurement on the apparatus. That's called Neumark's theorem. And so actually dealing with the projective case on a larger system is already sufficient to show that you can reproduce any update map. But it wouldn't teach you much for me to go through that whole calculation. So I'm just keeping it simple with this example. Are there questions?
Sorry, on a similar note, actually, I guess the problem that I have is how does one construct or justify how the different wave functions interact? Because there's no, you don't impose unitary for any reason.
Are you asking why should the unitary evolution take me to this particular, like from this state to this particular state?
Yeah, or why should the evolution be unitary? Because this. Yeah.
Why should the evolution be unitary?
Yeah, I mean in this interpretation, right?
Oh well, the Bohmian mechanics assumes that evolution of wave functions is totally unitary, and then all I'm doing here is I'm saying, suppose I've incorporated enough systems into consideration such that they form an isolated set. So by incorporating the environment, imagine that this now is an isolated system so that it is a good approximation to say that it evolves unitarily. And if I haven't done it, I can always find some more systems to incorporate such that it is a good approximation. And then the reason it has this particular evolution is basically because I'm assuming that this is a valid measurement. So a valid measurement always gets my apparatus carrying away information about the appropriate eigen state of the observable. So the reason I'm doing this particular unitary is because I'm imagining that the measurement actually is working. It's doing its job. And the reason I make these eta k's disjoint is an appeal to the kind of way that environmental decoherence works. So there's a whole lot of papers written about, well, let's take a very reasonable model of how a typical environment is going to interact with the system. Oh, look, it carries away information about position. So there I'm kind of just telling you that a lot of very reasonable models just do this. And it would be very contrived to imagine an environment that somehow didn't take away information about the system it was interacting with. Okay. So what I want to tell you a bit about is this idea for not making the assumption of a standard distribution of Bohmian positions. So this work started in some research done by a guy by the name of Anthony Valentini. So let me tell you what his concern with Bohmian mechanics was. So he noticed that the wave function is playing two very different roles. So you remember back in the first week we talked about ontic and epistemic concepts. So if you look at the wave function's role as a pilot wave, it's clearly ontic because it says if I imagine two universes that are described by different wave functions, then the Bohmian configuration in those two universes is going to evolve differently. And so clearly those different wave functions are describing different physics. I mean, explicitly we said they're part of the ontic state. But more than that, it's hard to imagine taking them out of the ontic state because the dynamics depends on the wave function. Yes?
Does Bohmian configuration mean zeta 1, zeta 2?
Exactly, yeah. So if I say Bohmian position, I just mean one particle. If I say Bohmian configuration, I mean a set of Bohmian positions of all the particles. So it seems to be playing an ontic role in the theory. But then on the other hand, you're told, oh, when you want to know what the distribution over the Bohmian configurations are, you just take psi squared. So now it seems to be playing an epistemic role. It tells you what any agent knows about the Bohmian configuration. And so Valentini thought that there's a tension here. You can't have this one object in the theory playing these two totally different roles. And in particular, if you think that all representations of epistemic concepts, like if I write down a probability distribution, that's saying something about what I believe about the system. It's really sort of describing something in my head. I wouldn't want the dynamics of a system in the world to depend on what I believe. That would kind of be crazy if what I believed about something actually influenced how it moved. So it would be odd if the pilot wave, if particles were guided by facts about what I believe about them. So Valentini was motivated to try to remove the epistemic aspect of the wave function and just make it have this ontic significance in the theory. And so he said, well, what if we started out with some other distribution besides the standard one? So for example, if this is the wave function squared in a two-dimensional space, then he says, well, suppose we start out with some other distribution, like this one here, for example. Then what he was able to show is that if you let these Bohmian particles evolve, in this case, I think it's just one particle in two dimensions, but you let it evolve under this guidance equation, over time, on a coarse-grained scale, it comes to match the psi-squared profile. And this is a bit like the H theorem in statistical mechanics. So what happens in Bohm mechanics is that if you look at the dynamics of the Bohmian positions, they tend to be very chaotic. And so the wave function defines a kind of velocity field. And the distribution of particles tends to respect the shape of the wave function because of this chaotic dynamics. I don't know if I can, in short order, do a good job of why the distribution should go over to this one on a coarse-grained scale. But this is a numerical simulation of what happens under Bohmian evolution for this kind of distribution. And it's pretty, so the wave function is imagined to evolve in a way that's periodic, so that the final wave function comes to respect the initial one. And now you see that the Bohmian positions are certainly going over to something that looks very much like psi-squared on a coarse-grained scale. So the idea is that the Bohmian positions come to equilibrate with the wave function. And once they've done that, then they respect the psi-squared distribution on a coarse-grained scale. So you don't need to assume that the original distribution was psi-squared to get this. So now your wave function can play a purely ontic role in the theory. Now I should say that this doesn't happen for all distributions you write down. There's a small set of exotic distributions that wouldn't give you this. So for example, if I put all of the weight on a node of the wave function, well then, its evolution wouldn't even be well defined. But for typical distributions, this is what occurs. And so Valentini proposes that this is actually what's going on. And what you find is that there are going to be deviations from the quantum predictions in this sort of model. Particularly if you could do some measurements on a very fine-grained scale, you might see the differences. You might see small deviations from the quantum predictions. And Valentini is motivated to try to propose scenarios where matter could have somehow not come to equilibrium. So he calls this kind of equilibration quantum equilibrium. And the question is, where might we find some matter in the universe that's outside of quantum equilibrium? And then if we test it and we do experiments on it, we'll see its statistics does not correspond to quantum theory. And then we would have vindicated this sort of model. So this, as I mentioned last time, is a nice example of how your interpretive strategy can lead to experimental predictions. So Valentini, because he was thinking about the Bohmian wave, was led to this particular suggestion of a theory that deviates from quantum theory. So his ideas are, for example, that maybe matter close to some exotic object like a black hole, where physics is not that well understood, maybe there we might expect that that matter hasn't equilibrated, and we might see that quantum theory is violated. So if you look at, for Valentini on the archive, you'll see a number of papers of that sort proposing ways that we might see this violation. Okay, questions about that? Okay, good. So I want to tell you a few things about, roughly speaking, contextuality in Bohmian mechanics. So I'm going to talk about whether measurements in the Bohmian theory actually reveal the properties that the particles have according to that interpretation. So suppose you look at the expectation value of some function of the position operator of the particle. Well, what you can find is that if you calculate the same expectation value now for the distribution of particle positions posited by Bohmian mechanics, so here I'm going to assume the standard distribution, and that same function of the Bohmian positions, you find equality. So your expectation value of position is just the expected value of the Bohmian position. And same for the position squared and the variance over position, etc. But if you look at the momentum, although the expectation value of the momentum operator is given by the expectation value of the Bohmian momentum in the distribution, if you look at something like the kinetic energy, which is the momentum operator squared, you find that it's not given by what you would have expected, namely the average of the kinetic energy of the Bohmian particles. It's something different that involves the wave function. And furthermore, when you ask, well, what is the relationship between this expectation value and the Bohmian position and the wave function of that particle, which are the ontic state of the system, the answer is it depends. It depends on the details of how you're trying to measure the momentum squared. So we saw last week that for a given operator, there may be many different measurement procedures, all of which are associated with the same Hermitian operator, so that they differ in context, but they're in the same operational equivalence class. And it could be that in your hidden variable model, or your ontological model, the way you represent the measurement actually depends on which context you're in. That's exactly what happens here. I can't tell you how the position and the wave function relate to this expectation value until you tell me how you're measuring it. What are the details of the procedure that you've done? OK, let me just say a couple more things about the energy. So if you say, well, what if we tried to define a Bohmian energy by looking at the sort of natural kinetic energy in Bohmian mechanics and the potential energy, but also include the quantum potential here? And if you look at the imaginary part of the Schrödinger equation, this term here is related to the partial derivative of the phase of the wave function with respect to time. And given that I know that energy eigenstates evolve as e to the I energy times time, it's not so crazy that this thing could be a good expression for the energy.
So we're choosing to define the energy such that it includes the quantum potential?
Yeah, it's just a sort of a proposal for what the energy might be, just to see, well, if we define the energy this way, does it make sense? Does it accord with our classical intuitions about what the energy of a system should be? And in an important sense, it doesn't, because you find that this quantity is not conserved as I evolve the configuration along its trajectory. But although it's not conserved on an individual trajectory, if I take an average of an ensemble of these guys, distributed according to the standard distribution, then I find, on average, it is conserved. And furthermore, it's given by the quantum expectation value of the total energy. So like position and momentum, this Hamiltonian operator in quantum theory, its expectation value can be understood as the expectation value of the same quantity for the Bohmian particles. But now we're starting to see that it's only the expectation values that are being reproduced here, and not what you would hope for. Like the particular members of the ensemble are not doing what you would expect. Energy is not conserved, for example. So you're already starting to see that in Bohmian mechanics, things at the operational level, where you're just looking at averages, are kind of behaving in a way that you might expect, like energy conservation. But at the deeper level, you're getting some surprising phenomena that aren't being revealed at the operational level. And we're going to see a lot of that. So let me give you an even more explicit example of contextuality. I already mentioned this dependence of how to represent the expectation value of the kinetic energy is context dependent, but I didn't really tell you why. I want to go to a much simpler example and explain how it works. So here's the example. I'm going to mention two measurements, which are extremely simple. So over here, I'm really doing a measurement on two modes, right? So there's a particle, and it's going to either enter this port or this port. You can imagine it as sort of being in the lower half plane or the upper half plane, if you like. And they're just going to be directed with mirrors to either this detector or this detector. And if I could draw this in the third dimension, these beams would not cross. Okay, so they pass over one another. And so these are not confined to a two-dimensional plane, whereas in this case, it's the same setup, but now these beams are confined to a two-dimensional plane, and they cross in space. OK, so if you ask, well, how are we going to represent this in operational quantum theory? So these detectors, by figuring out which of these two registers, I'm imagining there's just a single particle in this experiment. So by figuring out whether C or D locations are registered, that's just this measurement where phi is going to be the pure state corresponding to be in this region. And then prior to that, there's just some unitary that corresponds to this evolution, rectilinear evolution in this mirror. And so if I want to know what's the effective measurement of this whole box, that's a measurement on the particle at this time. Well, it's just the projectors onto the wave functions describing this guy and this guy. So pi c and pi d are the names they're going to give just to the overall projectors describing the two outcomes of this box, namely where you find the particle here at C or the particle here at D. And it just says that when you get C, you infer that the particle came in the B port, and when you get D, you infer that the particle came in the A port. So it's a really stupid measurement. It just does a binary position measurement. And similarly over here, nothing's changed. The only subtlety is that you have to remember that the unitary that propagates these wave functions forward, overlapping this 2D plane, doesn't care about the fact that they overlap. Right? So if I took a coherent superposition of a wave function here and a wave function here, and I propagated it forward according to hitting these mirrors in free evolution, unitary evolution is linear. So the way that phi a evolves doesn't depend at all on what coefficient there is on the phi b term. It could be 0, it could be 1/2. Doesn't matter. Phi a is going to evolve exactly the same way. And so this is exactly the same unitary, ultimately, as if these things didn't cross. And so when I get the C outcome, I also infer that I'm measuring projector onto the B port. And when I get the D outcome, I'm measuring the projector onto the A port. OK, so really sort of dull pair of measurements. Clearly, they're in the same operational equivalence class because they're represented by the same set of projectors. And any differences here is just a difference of context. And it seems like a really irrelevant difference of context. But it does make a big difference in Bohmian mechanics. So take the example where we feed in the particle in a wave function, which is a coherent superposition of a Gaussian wave packet at the A port and one at the B port, phi A and phi B. OK, well, if you work out what the Bohmian trajectories are for that wave function, right, you have to know the wave function to figure out what the guidance equation is to see how the particles move. So over here, the wave functions are disjoint everywhere because they never overlap in space. And so basically, the Bohmian position evolution is classical-like. It's just going to move rectilinearly in the way we would expect. But over here, where they overlap in space, because we have this no crossing of trajectories principle in Bohmian mechanics, they have to bounce off one another, like so. And so if you look at the statistics, right, for this wave function, half of the Bohmian trajectories are here and half are here, and you predict that you'll get half-half statistics for C and D. And here too, half the Bohmian positions are here, half are here, so you'll get the same statistics, half-half. So they predict exactly the same statistics. But if you then ask, what does getting outcome C tell me about the Bohmian position? Over here, it tells you it started at B, whereas over here, it tells you it started at A, which is surprising because you would expect that when you learn C, you would infer that the particle must have been over here. So what this means in the language of ontological models and response functions is if you say, what has learning C or D taught me about, for example, the Z coordinate of my Bohmian position? Well, here, learning C teaches me that the Z coordinate is over in the B region, so it's somewhere down here, and learning D teaches me it was in the A region, whereas here it's the opposite. And so we have an example where the response function depends on the context of the measurement, even though these guys are operationally equivalent, and that's an example of measurement contextuality. Is that clear? All right. So the position measurements always yield the statistics we would expect. So we saw that every moment of the position operator was reproduced in the corresponding moment of the distribution over the particle positions. But at the individual trajectories, it's not doing what we expect. And this kind of context here is not the kind that we saw showing up in those no-go theorems. So what we saw were, for example, when I measure in a three-dimensional space this vector together with two other vectors, well, that kind of context dependence can be turned into a proof of a contradiction, a proof that to interpret quantum theory, you need that kind of context dependence. This kind of context dependence is not strictly needed to avoid contradiction, but Bohmian mechanics has it nonetheless. And so you could say, as one criticism, that the deBroglie-Bohm interpretation actually has more contextuality than it strictly needs to have to avoid contradiction. It has to depend on these kinds of contexts. All right. So one thing I should mention is that when we talked about contextuality and non-locality, I tried to describe the kind of central mystery as a tension between the operational and the ontological levels. So in the case of non-locality, it was, why is it that we have faster than light causal influences, and yet we can't use them to send signals? Why do we have that sort of conspiratorial state of affairs? Why can't we use those influences to signal? And in a sense, Bohmian mechanics doesn't help resolve that tension. It just says that, well, if you're in this very special standard distribution, where the Bohmian particles are distributed according to psi squared, well then these causal influences, which exist in the model, we saw that we had a failure of local causality, they wash out at the operational level, and you can't use them to signal. And it has to be that you're in the standard distribution for that to occur. If you're outside the standard distribution, then you find you can use those causal influences to signal. So one of the predictions that Valentini's modification of Bohmian mechanics makes is not just that you'll see different statistics, but you'll be able to use that to send signals faster than the speed of light. And furthermore, in these, what we're going to see a little bit later, is that if you take a relativistic quantum field theory, then at the ontological level, Bohmian mechanics posits that there's some preferred rest frame, and signals are propagating faster than the speed of light relative to that preferred rest frame. But no observer can see those influences and use them to signal. So the whole theory at the operational level becomes Lorentz invariant. So again, you have this, just like we saw a failure of energy conservation at the ontological level, but a preservation at the operational level. We saw, superluminal influences at the ontological level, none at the operational level. Similarly with Lorentz invariance. Okay, so one response to this is that if you do buy into Valentini's approach, then once you find some non-standard distributions, the tension's gone. It says, yeah, it would be a problem if we had superluminal influence but no signaling. But actually, the situation is that we do have superluminal signaling, and so everything's fine. Except it may have been resolved in a way that you're not comfortable with, because it basically says that relativity theory is wrong, and there is a preferred rest frame. And even at the operational level, once we find this non-equilibrium matter, we'll be able to send these superluminal signals. And it turns out you can do a lot of other crazy stuff in these sorts of theories as well. So in quantum theory, you can't discriminate non-orthogonal states. In this theory, you can. People have tried to argue that in these sorts of theories, you also can do very hard computations that you can't do with quantum theory. And so it's actually a kind of a very powerful theory, Bohmian mechanics in the non-equilibrium distribution. Yes?
Right. This is probably answered a while ago, but if we accept the assumption about the standard distribution and respond to superluminal signaling criticism by saying we just cannot superluminally signal operationally because of expectation values. Why is it because our measurements are not fine enough?
That's right. The kinds of measurements you can do in Bohmian mechanics actually never allow you to learn the precise Bohmian position of things. So if you just look at what happens when you couple a system unitarily to an apparatus and figure out, what can I learn at the operational level, it never tells you about the precise Bohmian position. And so, yeah, there is a restriction on the measurements you can do, and that's what prevents you from using those superluminal influences to signal faster than light. You also have a restriction on how well you can prepare the distribution over Bohmian position. So, perhaps you could make, even with that limitation on the measurements, it's conceivable that by preparing precisely the Bohmian position, you could signal, but you're told that the only distributions over Bohmian position you can prepare are those that correspond to psi squared for some valid state psi. That's another restriction that this model imposes on you. Yes?
But is it a restriction or is it a consequence? It seems to be a consequence according to Valentini. You never need to specify it. It seems to be.
I see what you're saying. Well, Valentini would say in certain circumstances where the dynamics ensures equilibration, quantum equilibration, no matter what distribution you started with, you'll end up with the chi-square distribution. But Valentini will also say if we find some exotic matter that's outside of equilibrium, then we can use it to send signals. Yeah.
Another question. I was wondering. So I know that then I understand that Lorentz invariance arises as an effective symmetry of nature. But I'm wondering, can we understand it conceptually how it arises out of something non-Lorentz? Like, or is it not properly understood how? I mean, it's understood that it arises, but like a picture of how it arises, or is it just, I don't know.
It's a good question. If you ask the same question about just no signaling, how do we get no signaling despite the existence of these causal influences? I mean, I think by sort of looking at the calculation, you can sort of see how the appropriate averaging is done and how it all works out. But maybe it's better to describe it this way, that it's not as if people who've proposed the deBroglie-Bohm interpretation started with some postulates about how the world was and then derived operational quantum mechanics as a consequence. It's more that they started with the formalism of operational quantum mechanics and said, what sort of ontological picture of the world could I add to this and have it make sense? So what could I, what story can I tell that would explain these operational predictions? So in a way, they built their model to be Lorentz invariant and to be no signaling, because that's where they started effectively. I think if they had sort of a set of axioms that implied the Bohmian theory, and then that implied operational quantum mechanics, then it would be somehow more appropriate to say, well, which of those axioms ensures that we have certain features at the operational level that we don't see at the ontological level? But yeah, I don't know if I can really, maybe there's a better answer to that question. I just don't know what it is. Besides, going and looking at the calculation and seeing how it works. So like in the case of contextuality, you could ask, well, why is it that we see this dependence of the indicator functions, the response functions? They depend on the context, and yet the statistics don't. Well, it just has to do with the fact that I have 50-50 statistics, and it doesn't matter with 50-50 statistics. If I permute the two outcomes, it's still 50-50 statistics. So there you sort of see how you ensured that the statistics didn't depend on the context. And it sort of always works out that way. But I don't know if I can give a deeper reason. Other questions? Yes?
Yeah, if we go back to that example with the apparently extra contextuality. Okay.
Yeah.
What if you weighted your sort of incoming beams such that more came through A than is coming through B?
Mm-hmm. Like the initial wave function would now have a larger amplitude.
Would have a lot.
Right.
Yeah.
Yeah.
Then don't our statistics differ, because in one case D should be taking more, and then in the other case
No,
C should be taking
it doesn't, because what happens is that, so you put some more trajectories here and fewer trajectories here.
Yeah.
What you find is that some of these trajectories now go down. So you have, here we had all of them reflecting, but now you get some chunk of these going down, so that, yeah, the probability of D is the same as the probability of A. And now it's just that, okay, some of these guys go straight through to D. So when you find something at D, well, it means that perhaps it came from A, or perhaps it came from B. Whereas when you find it from C, it definitely came from A. But it does get statistics right. Did that make sense within that description? That I can have something that's non-crossing. It has to generate the right statistics, because I know that the standard distribution is observed. And so the way it does it is, if I just have a few of these, is that, does this work? Yeah, there's a bunch of them that go through, and they combine with these guys, like this. So let's say 2 of these go through, and so now I have 5 over here. Started with 5 over here, and then the rest, the rest get bounced off like that. So in this way, you can make sure that the statistics here are right, but there's still no crossing.
Okay.
So I mean, I could also use these examples to show contextuality. This one's just a little bit easier. Okay. Let's talk a little bit about the classical limit. So first of all, you can distinguish just a kind of operational classical limit. So if I said, suppose all your experimental operations are represented by density operators and POVMs that are all diagonal on some basis, well, then it all looks like classical probability theory. I mean, that kind of correspondence is easy to achieve, because as long as your interpretation reproduces operational quantum mechanics, then it'll reproduce operational quantum mechanics in those experiments where everything's diagonal. So it'll reproduce those kinds of classicality. We've already seen that Bohm mechanics does reproduce operational quantum mechanics. So that we can have. But if you say instead, well, no, hang on, classical mechanics doesn't only offer some predictions about what sorts of statistics we should see in experiments, it also offers an ontological picture of what's going on. And so the real role of a classical limit for a realist interpretation is to ask, is it the case that in some limit, the ontological picture of this interpretation goes over to the ontological picture that we know and love from classical theories? So I'll call that ontological correspondence. So I'm not going to spend much time on this, but what you can show is that there's a certain regime in which Bohm trajectories are Newtonian trajectories. And this is called the Ehrenfest regime. And it's probably a notion of classical limit that you've seen in undergraduate textbooks. The idea is that if you have a wave packet that is small compared to the length scale on which potentials are varying, then that wave packet sort of responds as a unit to the potential. And it sort of acts like a classical particle. The expectation value position just follows a classical Newtonian trajectory under the forces of all those potentials. And if you think of that wave packet as having some momentum and therefore some wavelength associated with it, it turns out that you can sort of define a characteristic scale L for your potentials. And as long as the wavelength of your wave packet is much less than L, then you're in this Ehrenfest regime where you expect to see classical dynamics. And in that same regime, you can show that the Bohm trajectories are all well approximated by Newtonian trajectories. Okay, so that's nice. But the problem is that there's certain cases where you aren't in the Ehrenfest regime. And this can even occur for systems that aren't microscopic. So it's not hard to come up with a scheme where you have a microscopic system that's not in the Ehrenfest regime. But even for macroscopic systems, you can get outside the Ehrenfest regime. And there's a very famous example due to Zurich and Paz, where they showed that effectively if you have chaotic dynamics, then you move out of the Ehrenfest regime very quickly. And in particular, there's a moon of Saturn called Hyperion, which is not spherical, and it's kind of tumbling in its orbit. And that's a chaotic dynamics. And then what they showed was that if you model that thing quantum mechanically and you imagine that it's isolated, then over an observable time scale, you would expect its wave packet to kind of disperse to an extent that it was no longer small in width compared to the length scale on which potentials are changing. I think the time scale was something like 10 years. So if the Hyperion were truly an isolated quantum system, then you might say, well, eventually we're going to start to see some deviations from the classical predictions. Now, it's going to turn out that decoherence saves the day because it's not isolated. But if you just ask, well, what if we set this thing up and have a macroscopic system, it's evolving chaotically on some time scale, it goes outside the Ehrenfest regime, what does Bohm mechanics say in that instance? And the problem is that it's going to have Bohm trajectories that are not like the Newtonian trajectories. Because if I have some wave packet that gets spread out and then maybe it starts interfering with itself, I'm going to have this no crossing phenomena for the Bohm trajectories, whereas the Newtonian trajectories don't have that feature. So I'm going to see actually a difference in the Bohm predictions of how this macroscopic object moves and the quantum predictions about how that same macroscopic object moves. But as I said, if you appeal to decoherence, you can salvage classical limit. So if you have decoherence in configuration space, so the environment is carrying away information about configuration, then that tends to eliminate these interference effects, and that tends to allow Bohm trajectories to cross. So what do I mean by that? Here's sort of a simple attempt to illustrate it. say I've got a system in 2D, and I'm interested in whether its Bohmian trajectories or its trajectories can cross in that two-dimensional space of the system alone. R2 here is going to be an environment that just has 1 degree of freedom. And the point is that if these two particles are approaching one another, if it turns out that their initial velocities can influence the position of the environment, so say it goes, if the initial velocity was this way, then it evolves to an R2 value that's larger than if the initial velocity was this way. So I imagine that these two guys start out in the same plane of R2, and now they're evolving to be separated. Well, if I projected all this and just looked at the R1 plane, that would appear like a trajectory crossing for the system alone. The point is that it's only once you specify a point in configuration space that the velocity is uniquely determined by the guidance equation. And it can be that by specifying a point in the configuration space of the first particle, well, there's still some freedom in specifying where it is in the configuration of the second particle. And so I can get an appearance of trajectory crossings for some subsystem. And so in that sense, I can reproduce Newtonian trajectories for the subsystem using this sort of coupling to an environment. All right. Let me talk about a few other notions of underdetermination, criticisms of Bohmian mechanics. So what do I mean by underdetermination? This is a term that philosophers use when you have many theories or models of reality that all give you the same predictions for experiments. So if you have many possible choices of ontological structure or dynamics that are consistent with the observations, you have an example of underdetermination of the theory by the observations. So okay, what's an example of that? So there's underdetermination of what are the supplementary variables, the variables that supplement the wave function in providing a complete description of reality. The standard approach is to take position. We said we supplement the wave function with Bohmian positions. And for a single particle, this was the scheme. And now let me just rewrite this in a particular way so that I can consider different supplementary variables. I can always write this guidance equation in terms of a probability current. So I can define a J probability current over space. And this is a formula that you might recognize from undergraduate textbooks in quantum theory for the probability current. You can derive it by just sort of working out the rate of change of psi squared in some region and asking to set that equal to the negative of the divergence of some probability current. And then you'll get this sort of expression for the probability current. So if you take the probability current over r squared, which is just psi squared, it turns out you can show that that is just grad s, this formula of grad s over m. So this is just another way of writing the guidance equation. OK, so now people have shown that you can do Bohmian mechanics differently. You can say, instead of taking the position to be preferred, I'll take the momentum to be preferred. So in particular, right after Bohm published his paper in 1952, Epstein came out with a response that said, you don't need to do this with position. You can do it with momentum instead. So the idea is that in addition to the wave function, there's a particle momentum which you have to specify. So usually the way this is formulated is you write the wave function in the momentum representation. And so then in momentum space, I am specifying a point, which is the momentum configuration of the particle, and some wave function over that space. And again, the trajectory through momentum space is going to be guided by this wave on momentum space. So the wave evolves according to the Schrödinger equation. I just have written it in the momentum representation here. And now these pi's, the Bohmian momenta, evolve by an analogous guidance equation, where this momentum probability current on the momentum space is again defined such that the divergence of this quantity gives me the rate of change of the probability of some momentum at a given point in momentum space. And I just divide that by r squared over the momentum space. And that tells me how the Bohmian momenta change over time. OK, so that's the proposal. And recently, Ward Stoiber, who was a postdoc here a few years back, has looked at this Epstein proposal. And he's gone in more depth and argued convincingly, I think, that it does reproduce the predictions of operational quantum theory. So you need to verify, for example, that in a typical measurement interaction with a typical environment, information about the system is carried away not only in the position degrees of freedom of the environment, but also in the momentum degrees of freedom. And that's not so inconceivable because, for example, where I see something in my visual field has something to do with the kind of wave vector of the light that enters my eye. That's a difference of momentum. So, all the kind of differences we see are distinguished in momentum space. And Stoiber has argued that all measurements are of this sort. Yes?
No. On the previous slide, you did represent psi in terms of the position representation, and that's allowed in quantum mechanics. Or sorry, you're represented in terms of momentum representation.
Mm-hmm.
That's allowed in quantum mechanics. Why is this ability to represent the guidance equation in the object state in terms of either position or momentum not just analogous to our ability to represent any wave function psi in any basis? Why is it a problem?
Well, if I'm doing operational quantum mechanics and I'm measuring some observable, suppose it's neither position nor momentum, it's just some observable, and I've prepared some state. Then I can say, well, you know what, I'm going to calculate the overlap of those guys in the position basis. So I'll represent this as a wave function of position, and I'll represent this in the position basis, and I'll do an integral over position. But I could equally well do that calculation in the momentum basis. So there it's really just a choice of a coordinate system. None of the predictions change. Whereas according to the proponents of the deBroglie-Bohm interpretation, this extra variable that you're introducing in addition to the wave function has physical significance. In the original formulation, the particle really is somewhere. They're making a statement about the way the world is. And so if somebody else comes along and says, no, I think the particle doesn't have a property of position, it has a property of momentum instead, that's the fundamental property, and the one whose equation of motion is first order and given by the wave function, then they're really saying this is a different theory. It might agree in its operational predictions, and in fact, that's what I'm arguing here, that it's going to make exactly the same predictions as operational quantum mechanics. And that was sort of the criterion for any realist interpretation. It should at least agree with those predictions. But you might say, well, these really are two different pictures of the world. The underdetermination criticism is that as soon as you can show that your strategy for adding a picture introduces things that actually don't have consequences, well, then that sort of undermines your particular strategy. So remember Plato's cave. The idea was that, well, if you introduce some extra structure like shape and it helps you explain the statistics, that's good. If you introduce color and it doesn't have any explanatory power, and you can imagine changing the color of the object and nothing changes in your shadows, then you think, well, perhaps that was not good science. And so the kind of criticism here is the fact that you can go back and forth between position as a supplementary variable and momentum and not change any predictions makes it seem like that extra supplementary variable is more like the color in Plato's cave analogy than it is like the shape, and therefore it kind of undermines the approach.
How come the ontological picture that involves position as a supplementary variable is not consistent with the ontological picture that involves momentum as a supplementary variable? Meaning,
how do we know that these are really sort of different pictures of the world as opposed to describing the same thing?
If there's a system that we can describe in terms of a Bohmian position, why can't, and we can alternatively describe it in terms of Bohmian momentum.
Yeah.
Why shouldn't we say that it has a Bohmian position and a Bohmian momentum?
Well, I guess when you look at how these theories reproduce the operational predictions, there's that whole business of one of the waves is occupied and the others are empty, and it's the occupied wave that gives you the result that you observe. If I said there's a Bohmian position and a Bohmian momentum, well then there's waves that are occupied relative to position, waves that are occupied relative to momentum. I can imagine that the position might tell me that the outcome is one thing, the momentum might tell me the outcome is another thing. Now I don't have a consistent interpretation. I might be able to do something different from these two models and say, here's a model that introduces both a position and a momentum, and here's how they evolve, and here's how I figure out which of the waves of the wave function is the one we see based on what the underlying position of momentum is. But then what you've done is introduce a third theory rather than show that these are just, theories that can be unified into one.
You said perhaps the occupied position wave would cause something different than the occupied momentum wave.
Mm-hmm.
Are you just saying maybe that happens, or do you know that that happens in the calculations?
Let's see. I have not looked at that carefully, so I can't say for certain that that happens, but I would expect that they would give different predictions.
So I wanted to clarify, when we describe a system that consists of multiple particles, so there's a Bohmian configuration, each zeta sub I, is that in the configuration space or real space? Or
So
is it
each
the R's?
one, like zeta sub 1, is a position in physical space. The vector zeta 1, zeta 2, zeta 3, that's in configuration space. Okay, let me move on. So if you look at the deBroglie Bohm, this is this momentum-based version of non-relativistic Bohmian mechanics. Is a very kind of crazy theory. It makes very we already saw that Bohmian mechanics has strange predictions about say the 1s orbital of the hydrogen atom where the thing just stays fixed. These kinds of trajectories are even stranger. But strictly speaking, it reproduces the operational predictions. An even simpler example of this is if you do a deBroglie Bohm theory of the electromagnetic field, say the free electromagnetic field, so people propose these sorts of things, then you have an even sort of harder problem deciding what the supplementary variables would be. Because the Hamiltonian involves the electric field and the magnetic field in equivalent ways, unlike position and momentum in a standard Hamiltonian, where they appear differently. So here you can choose to make electric fields, the electric field strength at every point your supplementary variable, or the magnetic field your supplementary variable, and either work fine. Yes?
So I understand there's indetermination, but I don't see how that would be analogous to the color in the potato case, because indeed the color has no explanatory power, but even if you can choose what variable you see as fundamental or something, there's still explanatory power that, because it explains Bohr's rule, explains collapse. So.
Yes. Perhaps you're right. That maybe that was being unfair to the Bohmians. Maybe a better analogy would be something like, you posit shape and it explains things, and then you have some sort of totally different idea which also explains the shadows. And now that you have these two models, it kind of undermines your confidence in both of them because there's sort of this ambiguity about what might be going on. Yes?
Yeah, I was wondering about, okay, so in the standard Bohmian mechanics, we've seen that the position of the particle in configuration space uniquely identifies the velocity, right? So why, I don't know, it seems to, so now when you have it in momentum space, why is it so, you could label it by the velocity, right? Because, every point in position space has unique velocity, has a velocity, probably not unique, but,
Right.
Yeah.
So you're saying that the original theory had a notion of momentum, just m times the rate of change of the Bohmian position.
Yes.
And you're saying what?
So
there's a momentum in that theory. How does it compare to the momentum in this theory?
Yes.
So the proponents of this momentum-based version, like if you read Stroiva's paper, he proposes a particular way of identifying positions, Bohmian positions for the particles in terms of this momentum variable. And he points out explicitly that in this theory, the relationship between momentum and position is not m times v. I don't know enough about the details of that to really explain how it works, but it's in Stroiva's paper, it's clear that this momentum that you're positing is not just m times the velocity of the other theory. And so maybe that actually, Nicole, answers your question about how you can see that these things really do make different predictions. This thing in Stroiva's paper that I can't reproduce today. Okay. So another example is spin. So it turns out that there's, I think somebody, a couple people yesterday were asking about spin. There are also multiple ways of modeling spin in deBroglie Bohm theory. And I'm not going to go into detail to these, just to point out ways in which there are underdeterminations. So one proposal by Bohm and collaborators is to make the supplementary variables not only the particle positions, but also some kind of orientation in space. So you imagine that the particle is some sort of extended rigid object, and it is actually evolving dynamically by rotating, and that contributes to the spin component. So it's sort of a very kind of literal interpretation of what spin might be. And you can show that under that model, you can reproduce the operational predictions. But John Bell showed that there's another way of doing it that also reproduces the operational predictions. It's a more minimalist approach because it just says, take just particle position as your supplementary variable. So there's no extra degree of freedom that corresponds to the spin. But now you still have an effect of the spin because relative to a theory without spin, your wave function is now a two-component wave function. And your guidance equation for the Bohmian positions is different now because it's given in terms of an expression of the phases in that two-component wave function. I think I might write that down on the next slide. But so the point is that the effect of the spin is seen in the dynamics of the particle positions. And when I do a measurement of the spin of a particle, I'm always encoding the outcome in the position of something. So it's not such a problem if there's no underlying spin degree of freedom. It's enough that things are assigned well-defined locations to explain what I observe in a measurement, according to Bell. So here's how the model works. So you've got now your two-component wave function and your particle position. The evolution equation for your two-component wave function is just a Pauli equation. So this is some vector potential and some magnetic field that the particle sees. This is the vector of Pauli matrices. And then the guidance equation is just a probability current over r squared, where the probability current now is the textbook probability current for the Pauli equation. So it involves this probability current expression for each component, spin component of the wave function, and it has this extra term involving the vector potential. So in that way, spin has its effect through the dynamical equation. But again, because we have these two models of spin, it's easy to wonder whether that's bad news for this interpretation. Same thing happens with quantum electrodynamics. So Bohm has a model of the free electromagnetic field where he takes the electric field to be the supplementary variable. I already mentioned that you could have taken the magnetic field. But now if you say, what can you do about the charges? Well, Bell had a model of fermions, basically where he imagined a lattice, and at every point in the lattice there was this variable that described the fermion number at that point. And he had an evolution equation, which, unlike everything we've seen thus far, was actually an indeterministic evolution equation. So all the other Bohmian models we've seen have been deterministic. But since then, Samuel Calin, who's also a postdoc here, has come up with a continuum version of Bell's model, which, if I recall correctly, is deterministic. And so you can combine either one of these guys with your model of the free electromagnetic field. And so now your supplementary variables are the electric field and the fermion numbers. And now you have a wave functional of the electric field and the fermion numbers that tells you how those things are going to evolve according to some guidance equation. All right. So an alternative to that is to do something like what Bell did for spin. So these guys, Ströbe and Westman, when they were both here, they were postdocs, showed that you can actually just get away with using a magnetic field or an electric field strength. And have no supplementary variables describing the charges. And you can still reproduce the predictions of operational quantum mechanics. And the idea here is that the field configuration, classically, always carries an image of where the charges are because of Gauss's law. So in a sense, describing the charges and describing the field, that gives you redundant information. So it's enough to know what the fields are. And so when I imagine that I'm observing some charge distribution, I can always understand that observation as an observation of the particular field configuration. And so it's possible to understand and reproduce the operational predictions by imagining that the whole world is really just made out of fields, and there are no charges. The only sense in which there's charges is as kind of imagined things which would satisfy Gauss's law for those fields. Anyhow, finally, let me tell you about another kind of an undetermination. I think we're running out of time, yeah. So the guidance equation isn't totally determined either. It turns out you can add a term to the guidance equation. So we're going back to the case of a non-relativistic particle, standard Bohm mechanics. Just add a term with a probability current that has no divergence. And it turns out you can show that this guidance equation also preserves the standard distribution and therefore reproduces the predictions of operational quantum theory. So the proof is straightforward. This is the proof I showed you last time, which established that if rho is equal to r squared at one time, then it stays equal to r squared at all times. So I define, this is the guidance equation, this is the formula for the probability current, and this is conservation of probability. Now, if I add this extra term in here with the divergenceless probability current, well, that's going to change the current density through V. And then when I take the gradient of the current density, instead of just grad S here, I'm going to have this extra term. But the divergence of that term is 0. So I get back to what I had before, and I have the same proof that rho remains r squared. So now it means that there's all these, for every divergenceless field, there's a new way of imagining how the Bohmian particles are moving. And at the end of the day, the statistics that this predicts are always the same. So at the operational level, all these theories look the same. But what's going on at the ontological level in terms of the particular dynamics is different. So in response to some of these criticisms, there's a few responses that are made. So you could say, well, for example, that extra divergenceless term, that's a less simple guidance equation. So if you just appeal to simplicity, you'd say use the one that has no extra term. Others have argued that certain symmetry principles can narrow down the choices of which guidance equation you use. So you might want invariance under certain symmetry transformations. And then finally, if you go Valentini's route of using non-standard distributions, then you can actually, if you can sort of see at the non-equilibrium level, you can start to distinguish those different choices of dynamics. Because now you don't have a standard distribution, and you'll be able to tell the difference between something that didn't have that extra current term and some theory that did. So that's always one way of getting out of this indetermination, to say, no, the standard distribution doesn't hold, and everything that's true at the ontological level actually has some signature at the operational level. All right, I just have a couple more things to say. So as I mentioned before, we have Bohm de Broglie interpretations of quantum electrodynamics, for example. As I mentioned, I haven't gone into them in great detail. But in those sorts of models, you find that the predictions at the operational level are Lorentz invariant. But at the ontological level, there's a preferred rest frame. There's influences that propagate faster than the speed of light relative to that preferred rest frame. So you don't have Lorentz invariance at the fundamental level. And it's a kind of underdetermination because the identity of the preferred rest frame is always hidden from you. Right? So there's no way to come to know that at the operational level. So one response is just, well, look, we have other examples of emergent symmetries. So although for a long time we've thought of Lorentz invariance as some sort of fundamental symmetry, maybe it's just an emergent symmetry, and it's fundamentally broken. That's happened before with other symmetries. It's just a statistical consequence of this particular quantum equilibrium distribution. And another response is that if, again, we find this non-equilibrium matter, then we will see explicitly in the operational predictions a failure of Lorentz invariant, which would vindicate this sort of approach. All right, so this is my last slide. There's sort of a commonality to all these sorts of criticisms we've seen. So the contextuality and non-locality that we know has to be in any realist interpretation are kind of hardwired into the de Broglie-Bohm interpretation. And there's more there than you strictly need to avoid contradiction. I would say the tension between no superluminal signaling and the existence of superluminal causes, and the same tension for contextuality, aren't really resolved. There's no good explanation of why we have these two facts in the theory. It's sort of built in because it's an interpretation of the operational theory. We have this underdetermination of the preferred variable in the form of the dynamics. Again, something that we don't see at the operational level, but there's a difference at the ontological level. And we get this difference about Lorentz invariance. And you can say these are all kind of failures of that methodological principle that I suggested was a good way to think about non-contextuality, which is that situations that are operationally not distinguishable should not be distinguished at the ontological level. That if you really can't tell the difference operationally, then maybe you should posit that physically these two scenarios are the same. So de Broglie-Bohm interpretation violates that kind of principle in spades. So all these different examples I've shown you could be thought of as examples of that. So that's it for the deBroglie Bohm interpretation. Tomorrow we're going to talk about collapse theories, and on Friday we're going to talk about many worlds.